Okay, so welcome everybody. Welcome, Stacy. I'm happy to have you here with us today. And so yeah, today's speaker is Steacy Coombs. Let me remove this. PhD. Well, as she's gonna say in a moment, she actually already defended her PhD, but she's still working at Queen's University, and she's gonna talk today about macromolecular migration in microfluidics. But before that, Stacy, tell us a bit more about yourself. Where are you from? What did you study before doing a PhD? And why did you do a PhD? And how did you find it? Things like that.
Yeah. So hi everyone. Nice to see you all today. So I am from Canada, from Guelph, Ontario. But I've been living in Kingston for the last 4 years for graduate school. So I did my master's first before my PhD. I did that 2020 to 2021. So I did it pretty quickly. I did it in about a year. And then I moved on to my PhD. And it was kind of more of a timing thing of why I did my PhD. That was like peak COVID season. And so when I started my master's, I was like, this is great. I'll do it for 2 years and then hopefully COVID will be over. Joke's on me. Um, but then Dr. Jackman, my supervisor, was like, no, you're doing your master's in a year and then you're going to do your PhD. And that is what happened. But I really enjoyed my research and it wasn't a compromise to do my PhD. I really, really enjoyed my work. Before my PhD, in my master's research, I was studying macromolecular branching um, and how to theoretically predict the behaviors of polymers. Um, and then into my PhD, I transitioned to microfluidics, which has been really great. And then for funding, so in Canada, you're guaranteed a certain amount of funding through your institution. And it's, partially funded by the government, and then the school picks up some of that as well. But I've also gotten some government scholarships that have helped me increase my funding as well as some external scholarships. So there's the Society of Plastics Engineers in the States that I've received funding from, which has really helped. And then I've also gotten involved with the university. So I work in student government, which also pays me every month, which is really wonderful. And I'm not sure if I missed any questions.
I don't think so. And so, well, before another question, I wanted to ask to you because I'm gonna ask this question to everybody. We have a trend for now. Usually when you do a PhD, you have three factors: the university, so where you do your PhD, the supervisor, and the subject. What's been the most important to you?
The most important to me was my supervisor. The One of the biggest reasons I wanted to do grad school was because I wanted to work with Dr. Jackman. Um, so I'd say that was the biggest thing for me. I picked Queen's because he was there, but also I had done my undergraduate degree at Queen's. I left to work for a bit, um, but coming back didn't really feel like that big of a deal because I had already been at Queen's for 5 years for my undergrad. So, but I would definitely say my supervisor was the biggest influence in my decision for graduate school.
I'm happy to hear that because that's the trend we are having for now. I don't know if people say that because these meetings are recorded. But no, I don't think so. And it's just good to see that people are still the most important factor in doing science.
Hmm.
And so you're not, from what you said before to me, before this meeting, you're not continuing in academia. You're going into industry.
Hmm.
So, I mean, the question is not really why. The question I want to ask you is more, is that something you had in mind before already? Is that just, I don't know, how this choice, sorry, came up?
Yeah, when I had started graduate school, I had really wanted to become a professor. That's the path that I wanted to follow. Um, but it's just tough. I think academia is tough right now. And life is really expensive. And so to do a postdoc, I am almost compromising a little bit, because you don't often get paid very much unless you're doing a very prestigious postdoc, which is hard to get. There aren't a ton of them, and I think there are quite a few in the States, but they are limited to American citizens. And so I'm Canadian, so that isn't a
Yeah.
great option for me. But it was also kind of, it depended on the opportunities that were available to me. There's a really great startup that I'm interested in being a part of, but kind of before they get off the ground, and I think they're gonna boom. And I'd really like to be a part of that. And so just the timing of things, that's what I want to do right now.
Well, best of luck
Thank
with
you.
that, Stacy. And with these, I think we can start the today's talk. I'll let you share your slides.
Here we go.
Great.
Okay, wonderful. So, hi again, everyone. This is pretty much my thesis presentation that I gave in December, with a few changes. But it is titled Macromolecular Migration and Microfluidics.
Stacy, I'm sorry to
Oh yeah.
interrupt you
Mhm.
immediately. People in general, if you have questions, do that in the chat, also during the talk,
Mm.
or raise your hand with the button on Zoom. And you should be able, Stacy, to see either the raised hands and chat, so you can, or I'm gonna just interrupt you if I see any question
Sure.
coming up. Okay.
Yeah, no problem. Thank you. Sorry, my dog is right beside me making noise. Come in. All right. So in our research group, we often study general rigid bead-rod theory and its ability to predict the rheological behaviors of polymers. Using this theory, when the macromolecule is replaced by identical spheres of fixed center-to-center separation, we call its replacement a rigid dumbbell. And we refer to this figure from the literature for the installation of molecular coordinates at the center of mass. From this, we are able to assign position vectors for each bead. Our group has often studied general rigid bead-rod theory using two different methods, with the first being structure by structure. So in the structure by structure method, we get our bead positions from each bead within each separate structure. So we would look at each of these structures separately. And from this, we are able to solve for our principal moments of inertia, architectural constants, shear viscosity, and relaxation time shown up here. In the second method, we have studied general rigid bead-rod theory analytically, meaning we begin with a geometric equation for a class of structures rather than a list of bead positions for each structure. During my master's, I was taking a course called Microscale Transport Phenomena that was motivated by the emerging fields of microfluidics and lab-on-chip technologies. I hadn't studied microfluidics before, but I wanted to connect it with the rheological work I had been studying using general rigid bead-rod theory. And we first found this connection in the works of Park and Fuller and their papers on confined geometries. We will be studying a specific branch of general rigid bead rod theory called rigid dumbbell theory. This is when we theoretically replace our polymer solution with a suspension of rigid dumbbells. We choose the rigid dumbbell suspension because it's the simplest relevant macromolecule. Our position vectors, principal moments of inertia, architectural constants, zero shear viscosity, and relaxation time are known for rigid dumbbells, which allow us to use the simple equations from general rigid bead rod theory. In this work, we have two main objectives. The first is exploring complex viscosity of polymer solutions in confinement in solution or in small amplitude oscillatory shear flow. And the second is to explore the lateral migration of these polymer solutions, polymer solutions within micro channels using these solutions predicted using rigid dumbbell theory. Today, we will start by discussing one of my publications, which you can find in Physics of Fluids, called Confinement and Complex Viscosity. And this is part one of my thesis. So from Park and Fuller's work, we are told that in small amplitude oscillatory shear flow, we subject the elastic liquid to a velocity gradient shown here. And from small amplitude oscillatory shear flow, we measure the Weisenberg number, or we mean that the Weisenberg number is less than 1.
Stacy, we have a question from Dr. Ashif Akram. It would be great if you could ask the question directly so we can interact more.
Can you hear me?
Yes.
Yeah.
Yeah. So I'm just trying to understand the setting of your problem. So in the previous figure, there is a rigid structure that you talked about earlier.
Mm-hmm.
You told that you are talking in the paradigm where these polymers are kind of these connected by these rigid rods, right?
Mm-hmm.
And what is the setting? Like what are you trying to calculate from this figure? I see that you are calculating velocity gradient. The velocity gradient of those. So you are treating the polymers as particles in a fluid. Is that correct?
That's correct.
And you are trying to find the velocity gradient along z direction, or maybe maybe you are doing that. Okay, because I can see that your function is z, t.
Mm-hmm. Yeah, so it would be in the x direction, and we're looking at complex viscosity. So we start with this velocity gradient, but part of this theory, that's just kind of the starting point for this theory, and we'll get to it in a moment, but we use
I can already see that this velocity is changing with z linearly. So it's increasing with increasing z. So there is a gradient of velocity in that sense. And your figure also alludes to that, because the arrow basically tells me the magnitude of Vx, I think, and that's increasing with increasing z. And at z equal to 0, it's 0. And then at negative z, it's decreasing. Or it's increasing in the opposite direction, as I understand it. So you are defining a parameter in the lower part of your slides, that is lambda gamma dot. Is that to the power 0 or some other to the power 2 square? I think that is that 0 or maybe some number, right? I don't know. Like I am not familiar with the literature.
I mean, as we move forward in this, make a little bit more sense. But this is just kind of a starting point for where we will get to in our main equations that we use for being able to predict complex viscosity in a
Gotcha.
microchannel.
So just before you move, just last question.
Yeah,
So
absolutely.
are you only talking about pure viscosity or viscoelasticity, for example? Or
We're talking about complex viscosity. So we're going to talk about the real part of the complex viscosity, so our viscous portion, and the imaginary part, the elastic.
Gotcha. So it's basically viscosity, not viscoelasticity.
Yeah.
Thank you.
Yeah. Thank you for that. And as I just said, we are going to look at complex viscosity. So the real part of the complex viscosity is eta prime, and this is our viscous portion. And then we have our eta double prime, which is our imaginary or elastic portion. And when the polymeric liquid touches the wall, the macromolecules near the wall reorient. And so long as the gap is large, the measured complex viscosity will be its bulk value and will just depend upon frequency, and its orientation distribution will satisfy the diffusion equation. However, if the gap is not large, then complex viscosity will depend upon both frequency and the macromolecular confinement, defined as epsilon sub f, where LP is the persistence length and B is half the confinement gap. Additionally, when the orientation distribution will depend on Z, which is the vertical position in the channel, and departs from the diffusion equation shown here. In this research, we focus specifically on complex viscosity measured as a function of confinement, and we have 3 levels of this confinement. The first is when epsilon is 0. This is when there is no confinement, also known as the bulk, meaning the persistence length is very small compared to the channel gap. The second is when epsilon is between 0 and 1. We call this small confinement, where the persistence length is about the same as the channel gap. And finally, when epsilon is greater than 1, this is large confinement, which is when the persistence length is much larger than the channel gap. From the literature, we can solve for complex viscosity of the bulk, which only depends on the Deborah number.
So,
Yeah,
Stacy, if I understand your characterization correctly, then the channel gap is basically the region along the z-axis which you are analyzing, right?
Yes.
Okay, fine.
Thank you. So for small confinement, we get our complex viscosity equations from Park's thesis, which we see depend upon both the Deborah number and confinement. And as the Deborah number goes to 0, we get the 0 shear viscosity, which we will use to normalize our complex viscosity equations. And here are the complex viscosity equations for large confinement as well. So we then plotted these equations for complex viscosity with the real part of the complex viscosity on the left and the imaginary part on the right. And we find that for suspension of rigid dumbbells, confinement increases as complex viscosity decreases at all frequencies. We then normalized our complex viscosity equations with the 0 shear for small confinement. And we did so for the bulk as well. So now we're going to compare our theory with experimental measurements. So our first worked example, we test our rigid dumbbell theory against experimental measurements from Davies and Stokes of complex modulus in the bulk and in small confinement. We assume that the bulk occurs at 199 microns and that small confinement occurs at 145 microns. We then converted this data to complex viscosity for a neutralized aqueous 0.15 weight % carbopol suspension at room temperature and fitted the real part of the complex viscosity with relaxation time, zero shear viscosity, and confinement. Here we have the fitting of our rigid dumbbell theory, where we find good agreement for the real part of the complex viscosity below a Deborah number of about 5. Our fitting confirms that the bulk occurs at 199 microns, and with it being equal to 0, seen in the red. And then we see that this again confirms that the small confinement occurs at 145 microns with epsilon equal to 0.6 with the blue. We then use these same fitted values for our imaginary part, but we do find an overprediction in the theory. For our second worked example, we collaborated with Dr. Pasquino at the University of Naples for measurements of atactic polystyrene solutions in confinement. We studied nearly monodispersed atactic polystyrene dissolved in diethyl phthalate at 3 concentrations in small amplitude oscillatory shear flow generated between parallel disks at varying gaps at constant frequency. Since this worked example is at a single frequency rather than a frequency sweep, we approach it a little bit differently. We evaluate our real part of the complex viscosity at epsilon equal to 0, so at our bulk, and rearrange to get an expression to solve for the relaxation time. We then fit our persistence length to the measured real part of the complex viscosity. And for all 3 of our polymer solutions, we find the real part of the complex viscosity decrease with confinement. And here is a summary table of our results from that fitting and some of our given results from that experimental measurements. And we do see that at all concentrations, our persistence length is the same. Now let's look at the imaginary part of the complex viscosity for this fitting. We could only see our concentration of our polystyrene solutions, or the concentrated polystyrene solution, because the imaginary part of the complex viscosity for our semi-dilute and threshold solutions was much smaller than the real part. So using our fitted values for the concentrated solution, we again find good qualitative agreement, but our rigid dumbbell theory overpredicts the imaginary part of the complex viscosity. In part 2 of this work, we continue our investigation of rigid dumbbell theory in confinement. However, instead of complex viscosity, we are looking at polymer migration. And I just wanted to stop. I'm not seeing any hands, but before I continue with this, was there any final questions about part 1? Oh, I see a hand.
Yes, that's me, Lucas.
Hi.
Stacy, just to make sure I get it right, the last term, it's coming from the rotational diffusion, right? It's an entropic effect.
For
the windows. For
sorry?
cases. For all cases, these elastic effects are all thermal fluctuations, just because of that, right? You orient them and they want to be randomically oriented.
Yeah, so in rigid dumbbell theory, we assume that it's the can't remember the right word. I'm blanking, but it's the architecture, the orientation of the polymer is the most important thing in rigid dumbbell theory, which we can see has some issues, but we do see good agreement in cases like this one.
Mm-hmm. Yeah. Okay. Okay. Perfect. Thanks.
Thank you. Okay. All right, I will move on. So this work.
There is a second question in chat.
Oh, I missed it.
What is the application of this problem?
Yeah. So we will be getting to it. It is a little bit later on. But this application, which we'll talk about in a bit, is figuring out how polymers flow within the microchannel. So this first part kind of gave us an understanding of what is actually happening within these microchannels. And as we move forward into part 2 and 3, we're actually going to look at the application within these microchannels. Thank you for the question. Okay. So, so this has also been published in Physics of Fluids as well. And in this work, we evaluate Stasiak and Cohen's analytical solution for orientational diffusion under laminar pressure-driven slot flow through a microchannel to design a microfluidic concentrator with 1 inlet and 3 outlets. For confined pressure-driven slot flow of a rigid dumbbell suspension, we start with the velocity profile for unconfined bulk flow, where V naught is the maximum velocity at the midplane of the microchannel. B is half the microchannel height, and Y over B is the dimensionless position along the vertical axis. From Stasiak and Cohen, we also have the migration velocity of rigid dumbbells, where epsilon is the product of confinement, which we non-dimensionalize for a dilute solution. Unlike in part 1, Stasiak and Cohen confinement is a product of the Weisenberg number and L over B. So there is a little bit of a difference. So in part 1, we had epsilon sub F, and in this case, we just have epsilon, just 2 different definitions of what confinement is. Now we want to know what's going on with the concentration of polymer once we have reached steady state. So we relate our migration velocity with dimensionless concentration. However, we want to not only non-dimensionalize this, but also normalize. We do this with the midplane concentration shown here, which gives us our main result for a dilute solution, which is capital XP. We graphed our dimensionless normalized dilute polymer concentration for varying Weisenberg number. At high confinement, which is our black line in all of the graphs, we see our polymer concentrated at the midplane. As confinement decreases and Weisenberg number increases, we see that the polymer is not as concentrated at the midplane. Now let's apply this theory to a worked example. Using arbitrary values for the dumbbell length, gap temperature, wall shear rate, bead diameter, and solvent viscosity, we can calculate the relaxation time for rigid dumbbells, which we can then determine the Weisenberg number and confinement using our equations. With our known Weisenberg number, we are able to plot our dimensionless normalized concentration curve with our XP equation, where we find that the complete fractionation position is 0.18. This process can be applied in the design of microfluidic channels if relaxation time and confinement are known. Which brings us to part 3 of this thesis. And my work in part 2 initiated me into designing and fabricating a physical microfluidic chip instead of just doing it with theory. I wanted to see, what's actually happening. Is this theory true? And so here are renderings of the 2 microfluidic chips I designed and fabricated with the square duct on the left and the slot flow on the right. And there are different ways to fabricate microfluidic chips, but we use the approach of soft lithography, which is commonly used for low production or prototyping. This fabrication started with designs in SolidWorks CAD software using a printer with UV sensitive resin. Molds for the microfluidic devices were printed. We then conducted siliconization, which forms a hydrophobic monolayer to prevent the PDMS adhesion. The PDMS was then mixed, degassed, and poured into the mold for curing. And to bond the PDMS surface to the glass microscope slide after demolding, plasma oxidation was conducted using a plasma cleaner. Our polymer solution that has initially been of interest is a solution of polyacrylamide and DI water. The water was selected due to polyacrylamide solubility and PDMS compatibility. Many common solvents used cause PDMS to swell, which destroys the channel geometry. For our microfluidic channels, one of the most important design variables is the length of the channel, since we need to ensure we give the polymer enough time to migrate. We measured the complex viscosity of our polymer solutions using a bobbin chip configuration, from which we get our relaxation time. We approximated that the residence time is about equal to the relaxation time using a flow rate of 1 microliter per minute, cross-sectional area of 90,000 micrometers squared, and accounting for error, we get a channel length of 0.8 centimeters. To confirm our migration theory, we need to measure the outlet concentrations of the outer 2 outlets and the midplane outlet using UV-Vis spectrophotometry to obtain absorbance versus wavelength plots, from which we would use the Lambert-Beer law to determine the concentrations of the 3 outlets. We're in the process of running these experiments and expect to see that the polymer is concentrated in outlet 2, and a lower or negligible amount of polymer is in outlet 1 and 3. It'd also be interesting to compare outlets 1 and 3, as they should be symmetrical. And this work has led to the discovery of 4 contributions of knowledge. First, we discovered that rigid dumbbell theory predicts confinement behaviors of polymer solutions. This allowed us to connect the transport properties of polymer solutions to microfluidic confinement. Secondly, we discovered that the persistence length of the polymer orientation does not depend on concentration. Thirdly, we discover analytical solutions for microfluidic macromolecular separation, where fractionation depends on channel gap and the Weisenberg number for dilute polymer solutions. Lastly, we discovered that the separation of polymer solution relies solely on orientational diffusion using simple microfluidic designs without the use of external forces. In my experimental work, I fabricated both slot flow and square duct channels. our rigid dumbbell theory presented here applies to slot flow polymer migration within a microchannel. As we expand our knowledge on rigid dumbbell theory for varying geometries, we'd also like to fabricate such microfluidic devices to continue to investigate polymer migration within these channels. And with that, I'd like to take a moment to thank my supervisors, Dr. Jackman and Dr. Escobedo, my group members, Dr. Mona Canzo, and collaborator, Dr. Pasquino, for their help during my studies, as well as to thank the Society of Plastics Engineers and NSERC for their financial support during my PhD. Thank you very much.
Thank you, Stacy.
Thank you, Stacy. That was great.
Yeah, that was a really nice talk. Has anyone has a question or can see in the chat? Can you see on the chat because I cannot open it?
Lucas is celebrating your talk. I have a non-related question. In the picture you had before with the people hanging the with the flags and everything, were you among them?
Oh, no, no. No, you can find
I'm
that.
asking that because I know you've been involved in a lot of things of your university.
Mhm.
Nice. What are those flags? I mean, Canadian, English, and what's the last one?
This is Queen's,
Okay.
the Queen's flag. I'm not sure.
There is a yellow one on the back. I don't know.
Oh, yeah. I'm not sure what that one is. I never even thought about it.
And okay, back to science. Is there anybody having more questions? First of all, I thank the people that ask questions during the talk, because that's a good thing to do.
Mhm.
Yeah, I just have some question. Like, I don't really understand how you choose your material to do those experiments. Like, you talked about a suspension with carbopol and something with polystyrene, but I didn't get really why you choose this one.
Yeah.
Those ones.
We started with the carbopol
Yeah.
because we couldn't find anything else. Like, we were looking for a very specific solution, because a lot of the research has to do with droplets or like individual molecules, and we wanted it to be a polymer solution, and we also needed it to not have any external forces in the results that are out there, and they're actually quite limited. And so that's why we started with the carbopol, because that's all we could find. And then we reached out to Dr. Pasquino for some help, and she often works with polystyrene, and that's just what she picked for that.
Okay.
And then as we moved to the research I'm doing now, with the polyacrylamide, we had actually started with polystyrene, but
yeah, it's just that I don't understand exactly what are the main differences in those things. Like, maybe the particles are a bit more rigid in certain case, I guess, and more elastic in other cases, more spherical. I don't know this material, so that's why I'm asking.
Yeah, I mean, as long as it is some sort of polymer solution that's compatible with PDMS, we were fine with using it. Yeah.
Okay, I see. With the whole, because every micro devices has some PDMS inside, like yours obviously, but maybe in industry it's exactly the same. I don't know. And so yeah.
And I know there are a lot of different ways to make microfluidic devices. You don't have to use PDMS. That's just what my research group does. And so we have to be careful with that. But I know there are other ways and other materials that you can use.
Okay, thank you. There is another question on the chat. That is, do you solve the boundary layer in the model? So yeah, because you didn't talk really about the boundary layer. layer in the channel. So I guess it's about that, but I don't know
Yeah,
exactly which
we
model
didn't do
they are.
anything. We didn't do anything with boundary layers. Do you want to talk more about that or explain it more?
I don't know. NH, can you describe a bit more? Because it's written on the chat and I don't, or maybe you can talk if you have the mic. I don't know.
That's okay.
I really don't know what to.
Email
Maybe
me. I'm happy to.
maybe they are writing. I don't know.
Oh, could be. Mhm.
Yeah, maybe.
May I?
Yeah.
I have some
Yeah.
questions. Sorry. I'm a little bit surprised that this rigid dumbbells model can predict fairly well the carboxyl particle suspensions.
Mhm.
Maybe because I don't know what exactly are these particles, carboxyl particles. How they are kind of anisotropic. They are not spherical in some sense.
Yeah, so yeah, the carbopol is it is a bit of a weird solution. But it really goes back to our rigid dumbbells. So the whole point of using this theory is trying to find the simplest theory that exists that can explain almost any polymer solution. And so with our rigid dumbbells, we're assuming that our polymer solution has become these rigid dumbbells in solution. So we know that's not actually what happens, but using our theory, that's what it's telling us. And so it doesn't matter what the macromolecular structure is of the actual solution. We're using this simple theory to explain what's happening without actually looking at what's going on in the actual solution.
I see. Yes. The result seems to agree impressively well.
Mhm.
I'm just honestly surprised that this rigid dumbbells model recovers apparently better than a regular elastic dumbbell with hook and springs. It was a surprise for me. I still don't see why one recovers better than the other.
Mhm. Yeah, and I haven't studied the elastic dumbbell at all. I know it's out there. But yeah, it is quite interesting that this simple model that's about rigid dumbbells can predict these solutions. It's really interesting.
Okay, no, perfect. Thank you.
Thank you.
Great talk, and I wish you the best.
Thank you.
Next.
Great. Any other questions? Okay, if that's so, I'm gonna stop the recording here.